In this video, we're going to look at Part A for the mock midterm for MATA22 for the summer semester. The first two questions are looking to see if you understand whether or not it's a linear operator. Here, the key here is to look at the type of expression that we have. Anytime we have a product of some kind or a constant plus one or something, that typically is an indication that we're not a linear operator. When we're not a linear operator, and often what we'll do is we'll ask you to show why it's not. So here what we could do is we could look at t of 0, 1 plus t of 1, 0. And this equals 0, 0 plus 0 minus 1, which equals 0 minus 1. But t of 1, 1 equals 1 minus 1. And these are not equal. So this is false. Here, this is true. And I encourage you to go through and prove to yourself that it's true by showing that T of CV plus W equals CT of V plus T of W. That would be well worth it to do that exercise. So because A1 is correct, we want the matrix representation for this expression in the standard basis. So we need to look at what T of E1 is, and this is T of 1, 0, which we showed, which we can show is 1, 0. And T of E2, which equals T of 0, 1, this equals 1, minus 1, minus 1. So my matrix representation is 1, minus 1, or 1, 0, minus 1, minus 1. Here, in A4, we are asked to compute the eigenvalues. And to do this, we're going to take the determinant of our matrix minus lambda. Now, this is a diagonal matrix, so really it's the determinant of these diagonal entries. So we get lambda minus 1, lambda minus 3, and lambda plus 2. So my eigenvalues are going to be 1, 3, and minus 2. Finally, we have we're asked to define two matrices A and B such that they're both invertible, but the sum is not invertible. Well, when doing this, I like to think of identity. So if I have the identity matrices, the identity matrix is invertible, and minus the identity is invertible. But when we add them together, we get 0, which is not invertible. So A equals 1, 0, 0, 1, and B equals minus 1, 0, 0, minus 1. Defining the rank nullity theorem is we have the dimension of the image of T plus the dimension of kernel of T equals the dimension of V. Suppose T is an injective linear transformation. What can we say about the nullity of T? Well, we have this theorem that where a linear transformation is injective if and only if the nullity of T equals 0. Here we showed in our last tutorial that if I have a diagonalizable matrix, if I look at the characteristic values of the matrix, if I look at the characteristic values of f applied to that matrix, this equals the set of f of lambda, where lambda is in the spectrum of the original matrix. So what I'm going to do is I'm going to apply f to each of these values. Now the eigenvalues of the original matrix are 4, minus 5, and 2. So f of 4 equals 4 cubed plus 2 times 4 minus 1, which equals 64 minus 8 minus 1, which equals 55. F of minus 5 equals minus 125 minus 10 minus 1, which equals minus 136. And f of 2 equals 8 plus 4 minus 1 equals 9. Oops, I'm not looking at the eigenvalues. I'm looking at f applied to these. So I look at that. F applied to A is F applied to these diagonal entries. I've done most of the work. I just was answering a different question. So this means that my matrix is 55, 0, minus 136, 0, 0, 0, 9. Okay. Now here I'm asking to compute a change of basis matrix. What's really nice about this is I look at what I does to 1, 2. This is 1, 2. Now I'm going to write 1, 2 in the standard basis, which is 1e1 plus 2e2. What does I do to 3 minus 1? It goes to 3 minus 1, which is 3e1 plus negative 1e2, meaning that the matrix representation of I, beta, e1, e2 is equal to 1, 2, 3 minus 1. Finally, we want to construct a non-diagonal transformation going from R2 to R2. When I think of this, I go 0, 1, 0, 0. I know this is not diagonalizable because it has the same, it's an upper triangular matrix with the same entries on the diagonal, but there is an upper diagonal piece. Knowing that this is not diagonalizable, I want to know what T of xy would give me this matrix representation. And here, if I multiply by the vector xy, it's going to give me y0. So my matrix representation, my linear transformation would be Txy equals y0. So that is my operator. I've gone through part A. I don't have, I don't think I will have time to go through any more of the questions, unfortunately. However, I will have lots of office hours on Thursday and on Friday morning. So if you have questions about any of the Part B questions, please, please, please feel free to drop by during office hours and I'll be happy to go through them.